Here is my Fourier Interactive program. It demonstrates the Fourier filtering using an image, and then we perform the Fourier transform. There's the transform. Then we do the inverse transform, and it gets back to the original image. Now I've got some sliders down here that, for example, this one sets an outer limit for a low pass filtering. That means that all of the values outside this range are set to 0. And then we do the inverse transform on what's left. And take a look at this inverse image as I bring this radius down and down and down. Watch the effect over here. This is the effect of low-pass filtering. Here we capture only the lowest frequencies, spatial frequencies of the image. Now we got another slider here that does kind of the opposite. It's a high-pass filter, so that any value that's below this threshold is zeroed out, except for the DC point right at the center. If you look over here, there's one pixel that remains on, and this high-pass filtering preserves the higher spatial frequencies of the image, and we can set this threshold wherever we want. And we can also do a band pass filtering by setting an outer and an inner limit. And this is the result of band pass filtering. There's a lock checkbox here that's supposed to lock these two radii together, but that part is not working, so forget about that for now. There is also an angular filtering feature. Sorry, let me get this threshold back to 0 and this to some reasonable level. And now if we do the angular threshold by raising this threshold, then what we have is a certain angular range of the Fourier transform is zeroed out, and you can set the actual angle of this. Now when we set it vertical, then what we see preserved in the image are horizontal components, such as this antenna and this horizon. And if we move the angle around, then you can see around about here where the filtering is the horizontal. Now it catches the vertical features such as these antennas, and the horizon is completely gone. But the real purpose of this video is to show you how to write this program. This is a Python script using matplotlib and numpy to speed up the computations of an example of how you can write a program like this, and hopefully you'll modify it to do whatever you need it to do. This program is available on my GitHub site, Slehar Fourier Interactive. So let's go on over. This is the program itself in Python. And we begin with imports, matplotlib .pyplot as PLT. This is what produces our user interface. And then we import numpy as NP, and we use numpy masks, numpy.ma as MA. And we import the Python image library, also called Pillow, and we'll import from that the image. And then we will import tkinter as TK. This is the interface that lets us get the file name. Here's tkinter.file dialog being imported. Now let's run this in debug mode. We've got a breakpoint over here. By the way, this interface is the Spyder interface, SPYDER. It inherits from MATLAB, this very convenient feature. In MATLAB, %sign is used as a comment marker, but in Python it's a hash. But if after the hash we then put a %, and then we add one more %, watch carefully, we get a whole line that just appears here. Show you again. And this helps visually segment your code. Very handy feature. This Spider interface also has a variable explorer among the different tabs here, and it has an interactive IPython console. Now let's run this program in debug mode. So we have a breakpoint over here, so we've executed the rad one, and just to demonstrate over here, there's a variable explorer, there's rad1, it's a floating point, value is 1. And now we'll just step through the program, step over, and see how as each line is executed, you see the variable explorer showing the values. Now here we have the tkinter, root equals tk. We're actually not going to have to use this one. There's nothing there, but you have to do that to set up the tkinter interface. If we go forward one more, we've executed root.withdraw, and if we look over here, the root has vanished. But now we're going to set an image file to be tk file dialog ask open file name. So this is how we'll set the input image. And then I've already got initial file value rover.png in the current directory. So when I step over this, we have the file name. Now we'll open the figure window. When X size and when Y size, these are in inches, so it's 16 inches across and 6 inches high. The win aspect we're going to need later on. And then this PLT close, when you're in debugging mode, every time you run, it creates a new copy of the program, and so I have this statement here to close all open programs to run this new one. All right, the fig equals plt dot figure with the fig size equals win X size, win Y size. And then we've got a fig soup title, that's super title, not subtitle, Fourier Interactive. Next, so here is our figure, 16 by 6. And then we continue. Now we're going to connect an event, the key press event, to the figure, and we will connect it through the function press. Where is press? Well, in Python script, you have to define functions before you could call them. So right here, immediately before it's called, we check to see if the event key is equal to Q, and if so, we close the program. Now we'll have the lock slider checkbox. Well, first we create an axis. This is not axis, but axes, the X and Y axes, and the rectangular area that it spans. And this is X origin and Y origin in relative values. So 0.2, 0.05, that's 0.2 across this span here, so that this will be about 0.2 over here. And in the Y direction, 0.05 of this vertical span, so that brings us to around here. Stepping forward, we're going to set the check button on clicked operation to func, and whereas func is right up here, so we have to define this. And if label equals locked, then slider locked equals, and this kind of checks to see whether there's an X in the box. Next, we set the axes for our 4 sliders here. Slider 1 is the radius 1 slider, slider 2, slider 3 is slider 4. In each case, we define, this one's the axes for slider 1 is fig.addAxes, and the X origin, Y origin, and then X size and Y size. This is where we will have the slider. And again, we don't need the X ticks and Y ticks, and then we'll set slider 2 and slider 3 and slider 4. Now we'll set an axis for the original image. So again, fig.addAxes, X and Y origin, width and height. Now we're going to read the image into a NumPy array. So we're going to start with image pill for the Python image library. Let me zoom this back up. Equals image.open, image file, which is the file name, .convert LA. L represents luminance or brightness and values from 0 to 255. And LA adds another alpha layer to that. Now, we'll convert this image pill into an image NP, a NumPy array, by calling numpy.array.imagePill .convert into luminance, so we don't need the alpha layer, and then divide by 255, so the values go from 0 to 1 instead of 0 to 255. And then we'll preserve the np.y size and x size from image np.shape. We'll also figure a half x, half y to represent the middle of the image. So now we'll assign the sliders. Slider 1 equals slider from axes of slider 1. Give it a label of R1, an initial value of 0, and then we've got npx size for how wide it will be, and value in it is 0. Likewise with slider 2. And now we're going to set rad1 and rad2 equal to slider 1 val and slider 2 val. Slider 3 angle, slider 4 threshold, angle thresh equals slider 3 val and slider 4 val respectively. Here's the axes for the Fourier image, X origin, Y origin, width and height. Set the tick marks to nothing and give it a title, Fourier. So now we compute the Fourier transform using the convenience NumPy functions. So we have an image NP, which was a NumPy version of our input image, and we're going to define a Fourier image as the NumPy.fft, the fast Fourier transform, .fft2, the two-dimensional version of it. And when we do this step, then let's take a look at Four image. This is the image that we just got. And I'm going to say show image. And there it is, this one here, figure 2. There's your Fourier transform image. It doesn't really look like much for various reasons. And then in the standard Fourier transform, the end result has got the quadrants swapped wrong. So here we'll have Fourier shift uses the numpy.fouriertransform.fft shift function that swaps the quadrants of the image. So here we go. We will step forward one, and let's see if we've got a Fourier shift here that will appear as an image. There it is. Still, we can't really see much of it. Back to the code. Now we'll do compute the Fourier log image. That's the log of the Fourier image. And here's Fourier log. We'll right click on that and show image. This time we see something. It uses its own color map. We'd rather have CMap equals gray, but this is just the Fourier image during our first pass through the computation. This pause here, I can't remember. I might have done that while debugging at some point. plt.set current axes, ax4, for plot equals plt.imshow the Fourier log image that we computed up here. This time we can set CMap equals gray and then plt show. And now we see the log of the Fourier transform is now visible. Now I'm going to show you Fourier filtering using the NumPy mesh grid concept. So here we have yy, xx equals np.meshgrid, mgrid, and we're going to do a mesh grid that goes from not 0 to y size and 0 to x size, but from minus half y to half y, and from minus half x to half x. Let's have a look at this image, yy and xx. Here's yy is right here, and if I right click and say show image, this here is the y dimension mesh grid. It's an image, every pixel of which reflects these values. Now you can see right down here, these are look at these values when I move the cursor, and it should go from minus half y, it says here 175, to half y. This is, sorry, this one's upside down, so the zeros at the top. So there's minus 178, and it comes down, 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 until you get to the center, and now it goes through 0, so the center of the image is here, and this goes down here. So every pixel in this image shows you the y value, and likewise, let's take a look at xx. Right click, show image, and it's the same thing, but this time horizontally, where it's from minus half y through 0 to half y. So these yy and xx are each complete images or mesh grid data structures. And now let's see how we can use these. This is how you use the mesh grid concept. So let's step forward one here and look at dist image. The distance image this is the square root of the sum of the squares. It's the distance formula. So let's have a look. It's alphabetical order. We want dist image. There it is. And right click in here and show image. Oh, it's hidden down here now. This is the dist image. So every pixel value here, if you see in the lower right here, is equal to the distance from the center, whatever direction you choose. So this is how you can replace a whole bunch of complicated code with a very simple formula. Now let's look at this. Angle image is the arctangent of YYXX. Let's have a look at that, step through, and let's see if we can find angle image up here. Angle image, show image. So this is every pixel in here is the arctangent of the angle. So over here, take a look at the bottom value in this corner, and here we have minus 3.1, that's minus pi, and it goes up and up as we go around, and then it gets to 0, and now we have positive values coming around here, and here we have plus pi. So every point in this image represents the arctangent of the angle from the center. Actually, we need to have this angle image flipped. Now, let's take a look at this next statement. The mask for the R1 is dist image greater than rad1. This here is a logical statement. The output of this is either true or false. Okay, let's get out of debug mode and just run the program normally, and we'll get some interesting mask values here, because you see what this piece of code is for doing the masks, and we'll set the angle, and let's see, how about threshold first, and then the angle, that's close to vertical. All right, now let's look at these values. R1 92, R2 142, angle is minus 1.5, and threshold is 0.3. Okay, so back to the filters sliders. The val init here for slider 1 will make that 92. And then the init val, we'll just call that 142. Then angle is minus 1.5. And the threshold is 0.3. All right, let's run the program again with these values. And there you see we have our thresholds all preset. Now, Command Q to quit. And so we'll set a breakpoint here and run in debug mode. And there, oh, isn't that, oh, well, okay. Yes, all right. Mask R1 equals distance image greater than rad1. And let's take a look at mask R1. Right click, show image. There it is. So here is mask R1. Now we'll go back to here and we'll step forward. There's mask R2, and let's take a look at, oops, I don't want that. I want right click, show image, and here we have mask R2. Now back to here, we'll say mask, step forward, mask radial equals numpy.logical and of mask R1 and mask R2. So let's find mask radial. Here it is, show image. And this here is the logical and between those two. Now, same thing with the angle. We'll step forward. Mask angle is this. Mask image is numpy.logical and between mask angle and mask radial. And here is where we set the DC point at the center of the Fourier image, that this center point will always be true. Then we step forward. Mask rad angle is over here, and show image. And there's mask rad angle. Then we'll step forward. Filt log for plot. Pause. Now we create the axes for the inverse Fourier image. We'll call it ax_four_inv is fig.add axes, and there we've got those. And then we'll remove the x ticks and the y ticks and set title inverse Fourier. So we'll step forward with the debugger. Now we do the inverse Fourier transform. And look how simple this is in NumPy. For I shift equals numpy.fft.ifft shift. This shifts the image in preparation for the inverse Fourier transform, working on an input of the filt image. Now we go forward to for inverse equals numpy.fft.ifft2, the inverse two-dimensional Fourier transform on the input of for I shift, the previous step. Then we go to for inverse real. We want the real version only, not the complex. So that's np.real. And the for inverse plot is plt.imshow, set current axes, inverse plot. Okay, we've gone through the whole process. As a first pass, we started with the original. We figured out the masks. Then we do the inverse transform on this filtered image, and there's the inverse Fourier. This program is now static. Nothing's happening, and it takes moving one of these sliders to make anything happen. So when you click any of these sliders, then it will immediately update the mask, do the inverse Fourier transform, and show you the result. Let's see how it does that. So here's our first pass that we've gone through, creating all the sliders, doing the Fourier filtering, and so forth. And we are now like right here. And now we define the update function. The update function is triggered if any of the sliders, these here are updates for the sliders. Each one of these, for example, slider 1, it will set rad1 equal to the slider value. Likewise, update 2 will set rad2 equals slider 2 value, and so forth with 3 and 4. But each one of these event callback functions calls the update function. What is the update function? Well, it's right here above. This is it. This is after you have touched a slider, then these mask R1 and mask R2 are recomputed, and the mask radial, mask angle, mask rad angle, and so forth. And then we say the filtered image is the Fourier shift times the masks that we just created here with the make mask command. Filt plot equals IMShow, plot set current axes. For I shift, this is the redoing the inverse Fourier transform, and then finding the real value, and then we plot it again. So there is the whole program. It is a script. I prefer scripts because they're simple, but it does not mean that it can't be object-oriented. This is a script that is highly object-oriented based on its dependence on MATLAB and NumPy. So in the Fourier transform, all of the computational intensity occurs inside this NumPy function, and where they have optimized very fast multiplication routines and functions. So this is an object-oriented Python script. I hope you find it useful. Download a version from my GitHub site. Make changes and let me know what you did. Thank you very much.